Good evening, boys and girls. Welcome to another lesson on Technical Sciences, grade 12. And we are studying a new topic completely, and that is momentum and impulse. Now, this is a topic that forms part of paper 1. It's a fairly easy topic, but it can get difficult if you do not practice it now and again. So, today we are going to make things as simple as possible for us to be able to understand what momentum is, as well as understand what impulse is. So, as per the norm, we are going to start with what is in the examination guidelines so that we are able to see what we are expected to know in this particular topic. So I also hope that you have your pens, your paper, and everything ready, and maybe a glass of water on the side so that you are able to then focus on this particular lesson. Right, so the lesson overview for today will be based on the examination guidelines, what we need to know in this particular topic. Then in features of the topic, we'll definitely be learning momentum and impulse, and we will be dealing with questions on momentum and impulse using a couple of examples, and also what is important in terms of the examination preparation and the number of marks that you can expect in this particular topic. Now, in this topic, you must be able to define the term momentum. And we define momentum as the product of an object's mass and its velocity. So it is the product of an object's mass and its velocity. And we will dwell more on that. You will see that when we calculate momentum, we actually take the mass of an object and we multiply by the velocity. Then we must be able to describe and really explain that linear momentum is a vector quantity and with the same direction as the velocity of the object. Right, so this already tells us that momentum is a vector quantity, and we remember that if it is a vector quantity, it means that it has both magnitude and direction. Then we must be able to calculate the momentum of a moving object using P is equal to mv in the context of technology. And you will see as we get into this particular topic, we will know that P represents the momentum, M represents the mass, and V represents the velocity of the object. Furthermore, this is what we need to know. We need to be able to state Newton's second law in terms of momentum. And we must be able to state that Newton's second law of motion in terms of momentum in weights. And when stated in weight, it says the net force acting on an object is equal to the rate of change of momentum of the object in the direction of the net force. Altogether, right? Then net force is equal to the rate of change in momentum, so its F net is equal to delta P over delta T. This is basically Newton's second law in terms of momentum formulae, but that is when it is stated in weights. Then we must be able to calculate the change in momentum when a resultant force acts on an object and its velocity. So, given the resultant force, which is the net force, and the velocity of the object, we must still be able to rather calculate the change in momentum of the object. Then, when we have when the velocity increases in the direction of the motion, When the velocity decreases, for example, that is when brakes are applied, when the object perhaps is reversing its direction of motion, like a soccer ball that is kicked back in the direction that it came from. So we will be talking about that. Furthermore, we will then talk about the conservation of momentum for elastic as well as inelastic collisions. And then we must be able to explain what is meant by an isolated system, and this we have done when we're doing Newton's laws of motion. We did it in the past week when we were dealing with work, energy, and power. So now we are still doing momentum, and we still talk about an isolated system. So we know that an isolated system is a system in which the net external force acting on the system is 0. And then we have, okay, we must still be able to then talk about what we mean when we talk about internal as well as external forces. Furthermore, we must be able to state the principle of conservation of linear momentum, which states that the total linear momentum of an isolated system remains constant in magnitude and direction. The total linear momentum of an isolated system remains constant in magnitude and direction. And we know for a fact that when you say it remains constant, we are basically saying it is conserved. And then we must be able to use the conservation of momentum, meaning the principle of conservation of linear momentum, to solve problems involving momentum in the context of technology. And we will only be dealing with problems that have two objects moving in one dimension along a straight line with the aid of an appropriate sign convention. So we will be taking direction into consideration. Yeah. In the next lessons, we will be distinguishing between elastic collisions as well as inelastic collisions, and we will do that in weights and also using a calculation. Right, so that is essentially what we need to know in terms of momentum. Now, what are we talking about when we talk about momentum? We know momentum is the product of mass and velocity of an object, or simply stated is the product of the object's mass and its velocity. Now, it is given by the formula P is equal to mv. So P is equal to m multiplied by v. Now, what does this mean, my dear learners? The P there stands for the momentum, and the unit for momentum is kilograms dot meter per second. And the dot there, my dear learners, it has to be there. So we measure momentum in kilograms dot meter per second, and the symbol is P. Again, remember that P has to be a small letter P. And the M in the formula represents the mass, and we know the mass must be measured in kilograms. Then the V represents the velocity, which is measured in meters per second. Right, so hence we say momentum is the product of the mass of an object and its velocity. Why the product? Why are we saying it is the product? It is the product because we are taking the mass and we are multiplying by the velocity. Right. Then we know that momentum is a vector quantity. Now, what do we mean when we say momentum is a vector quantity? It means it's a physical quantity that has both magnitude and direction. So when we ask you to calculate the momentum of an object, it means you need to give us both the magnitude as well as the direction. Right. So in our topic 3 now, I want us to look at an example. Now, here we have a car, and this car has a mass of 800 kilograms, and it moves with a velocity of 40 meters per second in a westerly direction. What is its momentum? So there we've been given the mass of the object, and we are happy it's in kilograms. We are given the velocity. We are also happy it is in meters per second. Now we want to know what is the momentum of the object. Right? To calculate that, we are going to say P is equal to mv. In other words, momentum is the product of the mass of an object and its velocity. For that formula, we are going to get a Mach. Then we substitute the mass, it's 800. We substitute the velocity, it's 40. And you can see that the velocity is substituted as positive. In other words, we are choosing west as positive. Then we find that our momentum gives us 32,000 kilograms dot meter per second west. So this would normally be 3 or 4 Machs. If it is 3 Machs, it means the final Mach is for the correct magnitude, including the direction. If it is 4 Machs, it means the magnitude of the momentum is given as 1 Mach and the direction is given as 1 Mach. Remember, my dear learners, we said you need to calculate the momentum. And when we say we want the momentum, and you know very well that momentum is a vector quantity, then you need to give us both magnitude and direction. Remember, we didn't just ask for the magnitude of the momentum. We asked for the momentum, which means you need to give us both magnitude and direction. Then before we get to the change in momentum, let us quickly talk about the momentum. Now we can see that the momentum depends on the mass and it depends on the velocity. So if I just increase the mass of the object, then the momentum is going to increase. Why? Because when I increase the mass of the object, the product of the mass and velocity increases, and that product is momentum. If I decrease the mass of this object, then momentum is going to decrease. Why? Because the product of this mass and velocity is going to decrease. And the same applies to the velocity. If you increase the velocity and you don't do anything to the mass, then the product will increase, so the momentum will increase. When you decrease the velocity and you keep the mass the same, still the product will increase, so the momentum will increase. If you increase both of them, then the product of mass and velocity will increase, so the momentum will also increase altogether. Right. Now, the momentum of an object can change. Now, what would cause the momentum of an object to change? That is if the speed of the object, or rather, that is if the velocity of the object increases or if the velocity of the object decreases altogether. Right. The mass of the object, we hardly deal with problems where the mass of the object decreases. So for your purposes, the mass of the object will remain constant, but the velocity of the object will be changing. For example, I could be having an object going from point A and going to point B. And when it's at point A, it's traveling at a speed of 20 meters per second. But when it's at point B, it's traveling at 35 meters per second. Now, what does this mean? It simply tells me that the momentum of the object here is not going to be the same as the momentum of the object at point B. And let us say it was an object that had a mass of 20 kilograms. So even when it's at point B, the mass is still going to be 20 kilograms. Now, what does this mean? You can definitely see that when the object is here, the product of the mass and the velocity, which is momentum, is 20 multiplied by 20, which will give you a certain value. But when you get to this point, the mass is still 20, but the velocity is 35 meters per second. So the product will be bigger than the product at A. In other words, the momentum at A, rather at B, will be larger than the momentum at A. What does that tell me? It tells me that the momentum of the object has changed. And why did the momentum of the object change? Because the velocity of the object changed. It actually increased from 20 meters per second to 35 meters per second. So the formula that we use to calculate the change in momentum is delta P is equal to mvf minus mvi, where you know your delta means the change. So the change in P, which means the change in momentum, is equal to the final momentum minus the initial momentum. Why final momentum minus initial momentum? Because here I'm taking the mass and I'm multiplying by the final velocity. So this is a product and therefore it will be the final momentum. Mass times initial velocity, it is a product, so it will be the initial momentum. Then what does this mean? It means that the M is the mass measured in kilograms. The VF is the final velocity measured in meters per second. The VI is the initial velocity measured in meters per second. So this is how you will get it in your formula sheet, and that is how you will calculate the change in momentum of an object. Right. Then here we have a situation. A boy hits a hockey ball, which is moving at 10 meters per second. So this is a value of V in an easterly direction. Now I will show you the importance of easterly in such a way that it moves faster in the same direction, that is at 12 meters per second. Right. Now they also told us that it is in the same direction. If the mass of the ball is 0.3 kilograms, calculate the change in the momentum of the ball. Now we need to understand that the momentum of the ball has actually changed. How do we know that the momentum of the ball has actually changed? Because the speed actually changed from 10 meters per second to 12 meters per second. So it means the momentum before is not the same as the momentum after. So we have the initial momentum and we have the final momentum. So we must get by how much did the momentum change? So let us answer that. Right. The direction stays the same. Therefore, it is positive. So we take the original direction to be positive. Now, the initial direction is normally positive, but it's up to you. You can still choose negative. But my advice there with that indication is to actually say, choose it as positive. Right. Now, the formula that we use to calculate the change in momentum is that one, and you will get it in your formula sheet. Delta P is equal to mvf minus mvi. Now, the mass of the ball did not change, so it is 0.3 kilograms. So in my substitution, I will say for the mass, it's 0.3. The final velocity is 12. Remember, before it was traveling at 10, so this is VI. Then after that, it was traveling at 12 meters per second, so that is VF. So there for VF, I will substitute the 12 minus, which comes from the formula there, it is, the mass is still 0.3, the initial velocity is 10, which is that one, the speed that it had before. Then you do your mathematics, you find that it gives you 0.6 kilograms dot meter per second. And because the value is positive, then it will mean east. It means we chose east as positive. Now, my dear learners, the mistake that we often see is that even if they told you that the object is moving east, some of the learners will actually write or take the direction to be to the right. If we use east, then you must use east, and the other direction will be west. If we use right, then you must use right, and the other direction will be left. So if you said 0.6 kilograms dot meter per second east, you will actually forfeit the mark for the direction. So 1 mark for the formula, 1 mark for the substitution, 1 mark for the correct magnitude of the momentum, of the change in momentum, and 1 mark for the direction. Sometimes it is 3 marks. When it is 3 marks, it means we are giving you a mark for both the magnitude and direction being correct. It means if any of those is incorrect, then you are going to forfeit marks. Right, so that is how we calculate the change in momentum, and we accept that there was a change in momentum because the velocity of the object actually changed. Now, let us look at this particular example. I have a ball with a mass of 500 grams, hits a wall with a velocity of 4 meters per second. So this is the velocity that it was traveling with initially. So this value represents the initial velocity. And after impact, meaning after colliding with the wall, or rather after hitting the wall, it moves away from the wall with a velocity of 3 meters per second. You then agree with me that this is the velocity after. So this value of 3 meters per second will represent the final velocity. Then we are required to calculate the change in the momentum of the ball. They didn't say we must get the momentum of the ball. They want the change in the momentum of the ball. Now, The momentum of the ball definitely has changed because the velocity has changed, but the mass did not change. So what can we see from here? Number one, the mass has been given in grams, so I am then forced to convert it to kilograms because the mass in that formula has to be substituted in kilograms. Then the velocity is fine, which is the initial velocity. And then they tell us after the impact, it moves away from the wall. So can you see that the directions are different? We actually have the ball going towards the wall. Ne? And secondly, after the impact, it goes in the opposite direction. In other words, the other direction now will be away from the wall. So the directions are different. And if the directions are different, remember, velocity is a vector. So I need to substitute it with direction. Now, what do I notice here? If one direction will be positive, then the other direction is going to be negative. So to calculate the change in the momentum of the ball, right? So this is what I would expect you to be able to do. Firstly, the momentum before is P is equal to mv, which is 0.5 multiplied by 4, right? So the mass is 0.5, and why is it 0.5? Because I took the 500 grams and I divided by 1,000. So if I divided by 1,000, then it would give me 0.5 kilograms. Hence there I have 0.5, and the initial velocity is 4 meters per second. So based on this diagram, you can see that I chose towards the wall as positive, and hence the initial velocity is a positive 4. So it's 2 kilograms dot meter per second, which is forward, or another learner could have just said this is towards the wall, right? Then the momentum that the object has after the collision is P is equal to m times the final velocity. The mass is 0.5 kilograms. The initial velocity, the final velocity is 3 meters per second. But now remember, it was going away from the wall. Hence it is negative. Right, so the negative means away from the wall. So I get negative 1.5 kilograms dot meter per second. And remember, you can't leave a vector negative, and you must always interpret direction. So that will give us 1.5 kilograms dot meter per second away from the wall. Now this is the momentum before, this is the momentum after. To get the change in momentum, you will say the change in momentum is mvf minus mvi, which is the final momentum, and the final momentum is negative 1.5. Remember, momentum is a vector, so we substitute it with direction, minus the initial momentum. That means the momentum when it was going towards the wall, remember it was a positive 2, and this in total, it will give us negative 3.5 kilograms dot meter per second. And remember, our vector must not be left negative, it must be positive. So it's 3.5 kilograms dot meter per second, and the negative means backwards, right? Remember, I'm interpreting that negative, so that's why I removed it there. And we know backwards there also means, just write it nicely there for you. We know the backward means away from the, it's actually away from the wall. I just want to write it in full. Another learner, you could have just done it straight away from this formula where delta P is equal to MVF minus MVI. Then you say the mass is 0.5. The final velocity, remember, it was 3 meters per second away from the wall, so it's a -3. This nicely. Right? Minus, which comes from the formula, the mass is still 0.5. Right, these are actually brackets. And the initial velocity, it was towards the wall, and it was 4, and it was a +4. Then you get your answer. It gives you -3.5 kilograms dot meter per second. And after you do that, you just take the same explanation there where we say you now have to interpret your change in momentum because it is a vector. So this is actually just going to come there altogether. So it will then be equal to 3.5 kilograms dot meter per second away from the wall. Do not leave your answer as a negative value. Then let me just erase this part so that we see our other questions clearly. There we go, there we go. Now, Susan hits a hockey ball with a mass of 150 grams, which is moving at 10 meters per second from behind with the hockey stick and changes the velocity of the ball to 12 meters per second in the same direction. Calculate the change in the momentum of the ball. Now we know the momentum has changed. Why? Because this is the speed before Susan hit it with a hockey stick. And we know this is the speed that the object has after it was hit with a hockey stick. And the direction does not change. So the hockey ball still goes in the same direction. So the momentum of the ball is definitely going to change because the initial velocity is not the same as the final velocity. And the mass is in grams. So we are then forced to convert it to kilograms. Now, let us answer that question. Now, this is what is happening. There, a ball was coming with a velocity of 10 meters per second, and then Susan had a hockey stick and hit the ball. So the ball continued in the same direction, but the velocity of the object increases. Now, pardon me where I said speed, because we are dealing with momentum, so we talk about velocity. So the velocity then increased, but the direction did not change. So to calculate the change in momentum, we'll say delta P is equal to MVF minus MVI. The mass, which was 150 grams, we then have to convert it to kilograms. In other words, we have to divide the 150 gram by 1,000, and this will give us 0.15 kilograms. Multiplied by the final velocity, which was 12. And I have chosen there to the right, which is the original direction, as positive. So it's a +12. You don't really have to include it, but If you include it, absolutely nothing wrong with that. Minus. This minus, remember, is from the formula itself. So there it is. Then the mass again is 0.15 and the initial velocity is 10. And remember, the direction was still the original direction, which was forward. So it's positive. Then you do your mathematics there. You find that you get 0.3 kilograms dot meter per second. And it's a positive value. In other words, it means it is in the same direction as the motion. Right. Then we go to 3.4.2. This time the ball is coming towards her with a velocity of 10 meters per second. And she brings the ball to rest with the hockey stick. Calculate the change in the momentum of the ball. Now there they tell us that it is brought to rest. In other words, the speed, or rather the velocity there, is 0 meters per second. Right. So this is a totally different scenario altogether. So Susan was in a field at some other point, and the ball came towards her with a velocity of 10 meters per second. In other words, the initial speed there is 10 meters per second, but this one is final velocity, which is 0 meters per second because he brought it to rest. So now we must calculate the change in the momentum of the ball. So the change in the momentum, right, is change in momentum is actually the change in M and V, which is M delta V. But put simply, you know that in your formula sheet, you will get it as MVF minus MVI. Then the mass is still 0.15. The final velocity is 0. Why? Because it was brought to rest. Now here I cannot substitute any sign. Why? Because if an object comes to rest, it's not moving in any direction. Minus the mass is 0.15 kilograms and the initial velocity is 10 meters per second when it was coming towards her. Then when you perform the calculation, you find that you get negative 1.5 kilograms dot meter per second. Then we know that we have to interpret the negative, we have to give the direction because we were asked for the change in momentum, not the magnitude. So it means we have to give both magnitude and direction. So this will give us 1.5 kilograms dot meter per second, but now the negative means it will be in the opposite direction as the motion. So this is essentially what happened when you look at the diagram. It was going towards Susan at 10 meters per second. So that was the initial velocity. And then with the hockey stick, she was able to bring it to rest. So the final velocity is 0 meters per second. Right. In the last scenario, which is 3.4.3, they tell us this time the ball moves towards Susan with a velocity of 10 meters per second. So again, at a different time during the game, it's going to her towards her at a velocity of 10 meters per second, but she hits the ball back to where it came from with a velocity of 12 meters per second. In other words, the velocity of the object changed, the mass remains the same, so it means the momentum of the object changed. So this gives us the final velocity of 12 meters per second. We are then asked to calculate the change in the momentum of the ball. Now, if it goes back to where it came from, it then tells me that it then moved in the opposite direction. So the direction the initial direction, which is the original direction, it was moving at 10 meters per second. Then the opposite direction, it was moving at 12 meters per second. So in a diagram, this is essentially what is happening. There's the object, it was moving at 10 meters per second towards her, which is the initial velocity. Then with the hockey stick, she hit it and it came back. It went back to the direction where it came from, which means the opposite direction at 12 meters per second. Then we are choosing the original direction to be positive. Then change in momentum, it's that, and simply put it's mvf minus mvi. The final mass is 0.15, which is the mass that it always had, times the final velocity, it's 12, but in the negative direction because this is in the opposite direction to the original motion. Minus, from the formula, the mass is still 0.15, and the original direction of motion, which is this one, it's 10, and it's a positive. Then we get the change in momentum to be negative 3.3 kilograms dot meter per second. And remember, we want the change in momentum, so we need to interpret the direction and not leave our vector negative. So this will be 3.3 kilograms dot meter per second in the opposite direction as the motion. Right. Now, I want us to then move to a concept that we refer to as impulse. And according to the examination guideline, we define impulse as it is the product of the net force acting on an object and the time the net force acts on the object. So it is the product, if you check there, it is the product of the net force acting on an object and the time the net force acts on an object. In other words, when you are looking at this, you are actually looking at impulse. So impulse is the product of the net force acting on the object and the time the net force acts on an object. So this entire product represents impulse. So in a formula, F net delta T is equal to delta P. So this is impulse. When you just look at one, it's F net. When you just look at the one, it's the change in time, which we call the contact time, the time the net force is acting on the object, but together as a product, it then gives you impulse. And that is equal to the change in momentum. So when you perform your calculations further, then you will say change in momentum is mvf minus mvi if we require you to calculate the impulse. So that is what we refer to as impulse. Now from this formula of impulse, we can see that we have F net, and we can actually try and state Newton's second law in terms of momentum, because there's a relationship there between F net and the time the net force is acting on the object, as well as the change in momentum. So we can then talk about Newton's second law in terms of momentum. So what I also wanted you to know there is that impulse is actually equal to the change in momentum. Why? Because all of that, the product of the net force acting on an object and the time the net force acts on an object is actually equal to the change in momentum. In other words, impulse is definitely equal to the change in momentum, which is the statement that I have written there for you. So how do we state Newton's second law in terms of momentum? We say the net force acting on an object is equal to the rate of change of momentum of the object in the direction of the net force. And why are we saying that? Because if you take that formula, F net delta T is equal to delta P. If you make F net the subject of the formula, then you will see that F net is actually going to be equal to delta P divided by delta T. In other words, the net force acting on an object is equal to the rate of change of momentum. The net force is not equal to the change in momentum. You can see that it's change in momentum divided by change in time. So it's the rate of change of momentum. So Newton's second law of motion in terms of momentum says the net force acting on an object is equal to the rate of change of momentum. That's what Newton's second law of motion is stated in terms of momentum. Now, let us look at a question. Here we have a tennis player, and the tennis player hits a tennis ball, and that tennis ball has a mass of 200 grams, which is moving towards him with a velocity of 20 meters per second east, and then back with a velocity of 30 meters per second west. Calculate the impulse of the ball. Now, this is what is happening. The tennis ball was moving towards the tennis player with a velocity of 20 meters per second. And the tennis player hit that particular tennis ball, and then it went back to the direction with which it came from, but then with a velocity of 30 meters per second. What we can note there is that there is a change in momentum. So we must get the net force. Rather, we must calculate the impulse on the ball. Now we are choosing the original direction, which is the eastern direction, which is east, as positive. In other words, west is going to be negative. Right. So to calculate that, we are going to say impulse is equal to the change in momentum, which is mvf minus mvi. But when you begin this, my dear learners, this I solely did it because I wanted you to see that impulse is actually equal to the change in momentum. But when you start your calculation, because we don't give you the formula like this, show us that F net delta T is actually equal to delta P. And after that, you can then say impulse, because we will award you a mark for that formula. Then you can then show us that by definition, impulse is the product of that net force acting on the object and the time the net force acts on an object. It's equal to the change in momentum, which is mvf minus mvi. The mass, which was 200 grams, right? Remember what we do? We will take the grams and we will divide by 1,000 because we want our mass to be in kilograms. So that will then give us 0.2 kilograms. The final velocity, which is 30 meters per second. And remember, now we are talking east. In other words, this direction will be west. In other words, we chose east as positive and west as negative. And hence, the final velocity is 30 meters per second west, which is negative, minus the mass, it's still 0.2. The final velocity, the initial velocity, which was east, is 20 meters per second. And remember, it is positive. Then we find our answer to give us negative 10 kilograms dot meter per second. Then we interpret our direction. It means it will be 10 kilograms dot meter per second. And remember that negative which we have omitted means west. So we will allocate a mark there, a mark there, a mark there, and a mark for all of that altogether. So this is more or less 4 marks. So the change in momentum, which represents the impulse, is then 10 kilograms dot meter per second west. Then we are then required to calculate the force of the racket, the force the racket will exert on the ball if the contact time is 0.2 seconds. Remember, when we say if the time of contact is 0.2 seconds, it means that is the time the net force was acting on the ball. Then I will use the formula impulse, which is F net delta T is equal to the change in momentum. Now the change in momentum, right? As always, you will just start it there. F net delta T is equal to delta P. So we are looking to calculate F net. And that is why we say F net, right? Then delta T, which is 0.2, the time of contact, is equal to the change in momentum we've already calculated. It was a negative 10. Remember, you have to substitute the negative. Why? Because momentum is a vector quantity. Then you do your mathematics, your F net will then be negative 50 newtons. In other words, when you start to interpret the negative, then by omitting it, it will be 50 newtons west, because the negative means west, and it makes sense that it was acting west. Right? So, based on the time that we have, when we meet again, we will then talk about the principle of conservation of linear momentum, which is what we call the law of conservation of momentum, of linear momentum. And that is when we will start to look at what happens to the total linear momentum if the system is isolated. So that is essentially what we are going to do in our follow-up lesson. But I quickly want to take you here. Right. And these are the exam tips. And remember now, this topic is going to count plus minus 22 marks in your final examination as well as your preparatory examination. So please make sure that you study it thoroughly. You will have about 4 marks in the multiple choice and 18 marks in your long questions, which are structured, or you could have 2 in multiple choice, 2 marks in multiple choice and 20 marks in long questions. But it's a fairly easy topic, and 22 marks is a lot. So that is all I had for you for today. As always, I always tell you, once you stop learning, remember you start dying. Thank you very much. Remember to send your questions that we will deal with in our question and answer session on Saturdays to stemdigitalschool@africateengigs.co.za. Thank you so much for tuning in. I hope that you have learned something and enjoy the rest of the evening. Thank you very much and good night.